Before we get into all of the wiring of this unit, I want to specifically cover this control board, also called an IFC for Integrated Furnace Control. This is the heart of the whole entire system. So if we see what's happening in this board first, then when we get to all the components, it should make a little bit more sense. So our main power is going to come in through where it says primary and neutral. So this is going to be our 110 volts. Then from there, we can send power to other locations. For example, we have XFMR, so a neutral and a black wire here for primary is going to send 120 volts to our transformer. When you send 120 volts to a transformer, it steps it down to 24 volts. It's going to come back over here to where it says SEC in common. This is going to be our secondary or low voltage side of our transformer. From there, it immediately goes into our fuse. And what's nice about this, the fuse is mounted straight into the control board, and it's going to be either a 3 amp fuse like this or a 6 amp fuse. Don't get this confused for a letter. It is 3, which is a number, and a 5, which is a number. Sometimes people look at these upside down and think it's an E or a 6, and that gets really confusing when you go to the supply house. So if you look on this fuse, there's this big black spot right here. It's burned out. Now there's a few ways you can check it. If it's powered up, you can check voltage across it. If you're reading voltage, then you have a blown fuse. If there's 0 volts, then you know the fuse is open. But I'm going to set my meter for ohms, and what we can do is actually check this. So before I check the fuse, I check my meter, I push the 2 leads together, and I can see how good my meter is working. And right now I'm showing some number of ohms for resistance. So that tells me my leads probably have some kind of a damage on there. So if I'm reading this number here being, oh, now we're reading 0 ohms. That's what it should show. So that means the switch is closed. It's a good fuse, or it will show OL and open. So if I check the fuse itself, it's saying OL. So we know that this fuse is open, or this is a bad fuse. If a fuse blows, you need to always be thinking, what caused it to blow? There's going to be some kind of a short in the system. Somewhere 2 wires are touching, or somewhere there's a wire touching ground. So don't ever just put a new fuse in until you find out the cause of it. So let's continue on with our list of components. Here we have where it says cool. This is the terminal that goes to our high speed for our fan motor. This relay right here actually controls this cooling terminal. We do work in the motor, we all come back to neutral. We have a separate relay controlling our heat. So this is going to be the speed used when we have the furnace running. We have another relay over here for fan. This is going to be continuous fan. If we leave the fanning on position, we can set whatever speed we want to keep the air circulating. It's only going to use one of these speeds at a time, and no matter what speed we use, it's all going to come back for 1 wire on the neutral. With the fan, we have this M1 and M2 terminals here. These are our unused terminals, and some boards they call it park. So these terminals don't go anywhere. So if I have an extra speed, we'll turn this over and see on the back side of the board, they don't go anywhere. Everything is connected on this board except for these terminals. They just sit there, they don't go anywhere. It's just a nice spot for us to hold the wires so we don't have an extra speed of a wire floating around, possibly shorting something out. Also in this board, I left out this where it says humidifier and EAC for electronic air cleaner. HUM for humidifier, so we'd have a wire here and another one going back to neutral. So this would be for an accessory for a humidifier. And then some units had an electronic air cleaner. So we would energize that from here and also neutral and run the accessories for that unit. So we're going to continue on. I'm going to turn this board so you can see it a little bit better. Here what we have is our spark igniter. This is a step up transformer. It's very little amperage, but it sets it up to high voltage so that you can actually spark and ignite the flames. These 2 terminals right here are going to go for inducer fan motor or forced draft motor. And here's the relay controlling this. This is high voltage. Here we're going to have a multiple plug system. This is going to control many of our accessories and safety switches. Most of this is all going to be low voltage controls here. And we've already covered our fuse. We're going to continue to turn this around. And on this side, this is where our thermostat wire is going to be. So C is for a common. Some of the digital thermostats now, you want to put the common wire in so that you make sure that you're powering the thermostat off the transformer. You have R for 24 volt power, you have W for heating, G for indoor fan, Y for a call for cooling. Now notice that I said the letter. Now you can put any color wire you want, but don't always think that red is going to be R. That's going to cause problems at some point in your career. Whatever wire I connect to R here, I also connect to R the thermostat. We also have this terminal here called twinning. So if I have two furnaces tied together, I would connect the twins on both of these so the control boards work in unison, they work together. If I'm doing what a thermostat does, I can connect any of the wires. I want to make a call for cooling, I connect a wire from R to Y to have a call for cooling. If I want to call for fan, I connect R to G. We run just the fan terminal over here. If I have a call for heat, I connect R to W. It's going to have a call for heat running through the heating sequence, but I never want to connect R to C. That's going to be a direct short, and it's going to blow this fuse out right here. Next thing I want to point out on this is these little dip switches. This is where you're going to have to RTFM, read the fabulous manual. What we're going to do with this is we use these dip switches in different combinations to adjust the fan off delay or many other options for this control board. And to move these dip switches, dual inline pair, you just simply push them back or forth, and the control board in the wiring is going to give you a specific reason for how you want to set these up. Also here we have several different lights. Checking a gas furnace, the first thing you want to do is look through the little window in the door to see what kind of lights are blinking. Because once you take the door off, it resets all the codes that it saved. So this is actually telling us if there's a flame, if we're okay, or if we have power. And if there's a problem, this light's going to blink so many times. Maybe it's 2 fast blinks and 2 slow blinks, or maybe it's just a steady 4 blinks in a row. There's 100 different combinations, but you have to find from the manufacturer what the blinks say, and it's going to give you an idea of what to check. The rest of the components on here are all just little capacitors, resistors, and the controls that making it think. If we're inspecting these units, we want to look on the back side. And this board, there's a significant amount of dust on here. What I usually do is take a paintbrush and clean these off. But if you look right here, we have a significant burnt spot right here on this control board. So something in some point in time has ruined this board, overheated it, shorted it out. It's literally burned these connections. So that's one of the things I look for in the back of the board, things like this or any other dark spots here. And I also want to look on the front side of the board to see is there any burnt spots on these boards, and that's a good indication that board is going to need to be replaced. Even if it's working right now, it could be under a certain sequence. It could be a safety component that's going to cause it to not to work, and you don't want to go out in the middle of the night to have to go solve that problem. Next thing we're going to do is cover all of what the wires do on this board. So here's all of the wires from this gas furnace. What I've done is I've separated them down, shortened them so we can easily see it. Now when I say easily see it, you're probably looking at all these wires and thinking, what in the world? But you don't look at all the wires at once. What we need to do is simplify it. We're going to break it down. If I'm looking at a map, I only want to look at the map of the streets that I need, how to get to where I need to go. I'm not going to look at every single street in a city. And the same thing here. I'm not looking at every single wire. I'm going to start specifically and look for one thing. What we're going to do is we're going to start with the power wires coming in. There's going to be 2 power wires coming in. This is going to be our 110 volts here. So this is particularly on what we call a pigtail or a plug. A lot of codes don't allow you to use this, but if you do have a plug, it's called ribbed to white, smooth to black. And this is a ribbed wire, and it connects to the white wire. And this wire is smooth, and it's connected to black. Ribbed to white, smooth to black. These 2 wires eventually get to our control board under primary and neutral. So if we follow the white wire, the neutral wire goes to the neutral terminal on our control board. But the black wire first makes a pit stop, and this is our door safety switch, also called our door interlock. So when the door is taken off, the switch opens and it kills power to everything on the control board. So this is wired in series into the switch, out of the switch, and it continues on to our primary of our control board. So now we've already eliminated 2 of those wires. We've really simplified it down. Now from there we can look at everything on here, but I specifically want to focus on the XFMR, just like we did when we talked about the control board. XFMR, short for transformer, and we have a neutral wire. So it's 2 wires going to power our transformer. So if I want to make sure my transformer is working, I can check here to see, am I getting 120 volts to my transformer? Now the job of the transformer is to step it from high voltage down to low voltage, or secondary voltage, or 24 volts. And I say 24 volts loosely because it could be anywhere from 18 volts down to, or up to 28 volts. So here's our secondary voltage, and it connects on the board where it says SCC. These 2 wires. 2 wires in, 2 wires out. So if I want to see, is my transformer working, I would check. I have 120 volts going to it, and I have 24 volts coming out of it. Then there, we immediately go into our fuse, and we have our thermostat connections. Now what I've done on the thermostat connections is I've connected from R to W. So when I energize this door switch, we're immediately going to have a call for heating. Now the next thing I want to point out is our blower motor. What I've done is put tape on here so when it's running you can see this moving. And it's really going to be 2 wires at a time. There's a lot of wires, but it's 2 at a time. We see high speed and neutral, 2 wires, or I can use the heating terminal from heating speed, which in this case probably a medium low, to neutral. Or if I want to have the fan circulating, this is low speed and neutral. And then over here I have my unused wire speed, which is probably a medium high and neutral. So I'm only using 2 wires at a time. Also for my fan motor, I'm using this capacitor. It's still 2 wires coming into a capacitor. It's very simple, 2 wires come in, 2 wires back out. So that's eliminated a good portion of this. Now we're going to go through a little bit more. These 2 plugs are actually following all the way to our inducer fan motor or our induced draft motor. 2 wires to the motor, so if I want to see if this motor is not working, do I have voltage to the motor? So it goes all the way back to here. Do you have voltage here? Yes. Do you have voltage here? Yes. Motor's not turning? Well, we have a bad motor. So we energize this motor. Now what's great about this motor is when it runs, it's pulling a vacuum. So it goes through a pressure switch over here. So it pulls a vacuum to this pressure switch. This pressure switch is just simply a switch. If we take this apart, we can see the hose is here. There's going to be a little spring that keeps this pushed up. If we look at this pressure switch and we take it apart, we see the hose hooks into the side and there's a spring in here that keeps this pushed up. And this is nothing more than a little micro switch right here. So what happens is this switch is normally open and we pull a vacuum, then the switch closes and it just connects these 2 wires. Again, 2 wires. So when this motor runs, it pulls a vacuum to our pressure switch. The switch closes, connects these 2 wires. If we follow these 2 wires, we go back to this plug outlet right here. So this plug is sending 24 volts through one of the wires and is waiting to see if we get 24 volts back to the other wire. This whole job of this switch is to make sure this motor is not just running, but also pulling the proper vacuum or draft through the heat exchanger. This switch is supposed to close at 0.30 inches of water column negative pressure. So what I've done is added a T in here and added a component which is called a magnehelix. There's digital versions of these, but it's still going to measure our vacuum. So when this motor is running, we're going to see how much inches of water column I have to see if this switch is going to have enough vacuum to close. Now if I want to check this switch, I can see with my meter, I can put my meter in the 2 points. If I'm getting 24 volts, the switch is open. If I'm getting 0 volts, the switch is closed. So it's still, again, just 2 wires in. Over here we have 2 more wires going to this multiple plug, but it's 2 wires and it wires in series through multiple limits. We go into, out of, into, out of, into, out of, into, out of, and all the way back home. So it's 2 wires, again, 2 wires, 2 wires, 2 wires, and 2 wires. Quite simple. These are limit switches, they're manual limits, and these are specifically rollouts. So if the flame was to roll out of the heat exchanger, it would cause this bimetal to trip. When the bimetal tripped, then it's going to open the wires and the control board knows that one of these safeties have failed. When we come out, we push this button and it resets it, but if the flame rolled out of the heat exchanger, we want to know why before we just press that button. This is our primary limit. If this one fails, you need to be thinking airflow, airflow, airflow. Something with the airflow. We're not getting enough airflow. This one automatically resets itself. So again, it's 2 wires, quite simple. Now we're going to look over for our combination gas valve. Now what I've done with the combination gas valve is completely separated it. This is nothing more than a solenoid valve. And if we look here, we can see it's an electromagnet. Even though you're looking at copper wires, each one of these have a coating on it. So the electrons go in a circle, creating an electromagnet when it's energized. And the spring keeps it pushed down. This is the valve for a combination gas valve. Now, this is a pressure regulator, which we'll talk a little bit about later. But 2 wires energize this electromagnet. This is a 24 volt valve, and if we follow these 2 wires, it goes to a double pole switch. This switch is also another safety switch. This particular switch is an auxiliary limit switch on the blower housing. So if this gets too hot, it actually breaks both of the wires to the switch. So 2 wires in, 2 wires back out to this multi-plug. So now we've gone through almost every single wire, and it's 2 wires, 2 wires, and 2 wires, except for here we have a single wire coming out of this plug. This wire is going to our flame sensor. So the flame sensor proves a flame through a process called flame rectification. The flames actually convert this from an AC current to a pulsating DC current, and the control board reads that through the ground wire. And here we have our ground wire connected to this board, and there's also a green ground wire here connecting it to our board. So that has only one wire. Since this is a direct spark ignition unit, we also have another one single wire coming from our step-up transformer. This one single wire comes over here, and it goes through this porcelain and arcs to the second terminal, which is grounded also to the board. So when we energize this, you're going to see some sparking happening right here. So what we're going to do is we're going to energize this unit and have it run and go through most of the sequence. Now, since I don't have a flame, it's going to stop at this point and go back through its safeties. But once this motor starts running, it's going to be a little bit loud and it may be difficult to hear. We're going to see this motor run, pull a vacuum here. We're going to see how much pressure we have. This switch is going to close to the control board. These switches are already closed. Then it's going to energize our spark igniter and also energize this electromagnet, the solenoid, at the same time. Since we don't have a flame, then we'll stop igniting and it's going to release the electromagnet and this is going to pop right back out. And it will do that one more time before it goes into a safety, and it's going to keep this motor running and turn this fan on. But let's see exactly what happens. Now this switch is broken, so when I push this in, it's going to hold it, which works great for this demonstration, but this switch really would need to be replaced on an actual unit. So here we're going to energize this. Immediately our inducer fan motor comes on. We pull a vacuum. We're pulling more. We need 0.3. We're at 0.4, so that's good. This switch closes, sends 24 volts back to the IFC. It's going to let this run, the pre-purge the heat exchanger, and then the IFC is going to energize this step-up transformer, which is going to have a little spark happening over here. And at the same time, it's going to send 24 volts through this switch to energize our electromagnet, and that's going to pull in. So if we wait shortly, it's going to start energizing. Here there's a spark happening, and you notice it's pulled in. A few seconds of no flame. We're going to end our spark, and that's going to pop right back out. So it said, hey, there's no flame. We go into a safety. Now I can check my voltage. The bottom number here is going to be voltage. I turn it to volts. Turn it to volts. The very bottom number down here is going to be voltage. Top number is amps. So the voltage to this unit, if I can check, if I can pull these wires back a little bit and check voltage to our motor. So I'm getting 123 volts to the motor, and this motor is pulling 0.4 into the water column vacuum through the heat exchanger. I can also check the amperage on this motor. The top number is going to be amps, and if I clamp it around this wire here, I'm reading 1.4 amps, and if I clamp it around the other wire, 1.5 amps. It's pretty close to the same, so I know that my amps are going through here. Now, is that enough amps? We have to compare it to the tag of the motor. We want to make sure this amperage is under the amps here. We see our spark igniter engaging, no flame, so it kicked it back out. So now I can check voltage to my combination gas valve. And I have to wait for the proper sequence. So the fan motor is running, I have my vacuum, this switch is closed. So if I want to see if I'm getting 24 volts on my combination gas valve, I do the same thing. I want to press one of my terminals on this side and one on this side. When I do this, I need to be careful that I don't short across those two terminals. So I'm going to press one here and one here. And if I look, I'm getting 0 volts. We wait for the correct sequence. Now I'm getting 26 volts, and you can see it's pulled in. So I'm having the correct voltage, and it pulls in. It doesn't mean that I'm going to have a flame, though. You got to remember it's a combination of a solenoid valve, which is this, and the pressure regulator. The pressure regulator reduces the pressure coming in to the correct 3.5 inches of water column coming out for most natural gas furnaces. So you need to see, do you have pressure coming in? Maybe the customer didn't pay their gas bill. So do you have the correct pressure in? And also see if you have pressure coming out. So if you have pressure coming in and you don't have any pressure coming out and you have 24 volts here, that means that this is stuck and it's not actually opening. So you have to diagnose this in 2 steps. It's a solenoid valve and also a pressure regulator. I had an employee of mine that went to a customer's house and said they had a bad combination gas valve when in reality They didn't have gas to the house. So even though this solenoid switch was opening, there was no gas to flow through it. So now we've broken down these 2-wire components. Notice I didn't have 24 volts entirely, only in the correct sequence. So next we're going to check this pressure switch and see what's happening with our pressure switch. So we're going to re-energize the system again. We can see we're pulling a vacuum. The switch should be closed. So I'm going to check my voltage. So next we're going to check this pressure switch. So what I'm going to do with this is you're going to see my meter. We're going to check voltage. And I'm going to put my meter on one terminal here and the other side here. And we have a call for heating. I have 27 volts. But once I get enough pressure over here, this switch closes. And when this switch closes, we have 0 volts. So I know that the switch is closed. So it's a 2-part. Do I have this switch closed? And if it's not closed, do I have enough pressure? So if you do have enough pressure and the switch is not closing, you have a bad switch. If the switch is not closing and you don't have enough pressure, maybe it's the hose, maybe it's this fan motor in here, maybe something's happening, maybe this motor's not working, but you have to make sure it's 2 parts. I'm pulling a vacuum for that switch to close. That switch closes, the IFC knows, open the gas valve, energize the spark igniter, no flame, so it shuts off the spark igniter and closes the combination gas valve. It's a pretty simple little sequence. It's a pretty nice sequence. So what we're going to do next, I'm going to take the jumper off for our call for heating. So now when I energize my control board, nothing should happen because my thermostat's not doing anything. So I know that I'm getting 120 volts to my board because I can again use my meter. So the bottom number is voltage, and I check between my neutral and my primary, and it shows I'm getting 123 volts to my control board. So what would happen though if one of our limit switches failed? So what I'm going to do is I'm going to manually trip this limit. Now this limits the rollout. If the flame was to roll out, it's going to be a big issue. So we're going to manually push this in. You see the control board did 2 things. It immediately energized our combustion fan motor, or inducer draft motor, to force the draft to that heat exchanger to protect it. It also is energizing our blower motor to move air across the heat exchanger so it cools off. Because it doesn't know if it's one of these or one of those, so as a safety factor, that's what it does. Now when we go to the customer's house, what we want to do is look at the control board and see what kind of code it's blinking. Here it's blinking a very specific code. In this case, what we can do is we can check all these limits individually with voltage. So I have my meter on voltage, and if the switch is closed, it should read 0 volts. And if the switch is open, it should read 24 volts. So if I check across this switch here, reading 27 volts. 27 volts, we know that switch is open. Now an easier way is you can just simply press the button and it resets it. So if we check across, we see that we have now 0 volts. So the switch is now closed. Faster way, instead of checking each individual one, you would just simply press all of those and make sure that they are all closed. You do this the same way. You can check voltage. If you're reading voltage, that switch is open. If you're not reading voltage, that is closed. Now again, if you have a main limit switch that fails, you need to be thinking airflow. But it is possible for water to leak from the evaporator coil and cause these to completely corrode up. So everything is simply 2 wires, 2 wires, and 2 wires. Now we're going to take a look over here at the blower motor side. So next we're going to check the speeds on the motor. So if I check my unused speed, I have 0 amps, the top one. And if I check low speed, I have 0 amps. That's for my fan circulating. And if I check the heating terminal, I end up with 0 amps, so it's not working. And if I check my high speed, 0 amps. And so if I check my common side, my neutral side, I also have 0 amps. So 0 amps means this motor should be working. If we look and see, the motor's definitely not working. So what we're going to do is we're going to have a call for fan. So when a thermostat calls for fan, it's going to connect R to G. G stands for indoor fan relay. So I'm going to do that very thing. But what I'm going to do is clamp around this common wire. And if you look at this very top number here, let's see if I can turn the light on. And we're going to jumper this so the fan will come on. You'll start seeing a flow of amperage. So we're going to connect from R to G. And what that should do is energize, let's see, for fan, this relay is going to energize this speed. And we can see we're pulling 1.49 amps through the common side. Now if I wanted to see what speed is really being used, I can also check my high speed, 0 amps. I check my medium low or heating speed, 0 amps. And if I check the side for fan or circulate, I end up with 1.5 amps. So we know that's the speed being used, and my unused speed, 0 amps, so it's also not being used. So what we're going to do next is I'm going to call for cooling. When I have the thermostat call for cooling, it's going to connect R to Y. Then we're going to energize the speed for cooling, which is going to be this relay, and it's going to energize high speed. So I'm going to clamp the meter around high speed, and right now we see that there's 0 amps. But when I connect R to Y, we hear a click, and here I'm pulling 5.6 amps. So I'm using more amps, a higher speed of the motor. And we also check the neutral side, and we see that there is also 5.6 amps. So we know that high speed is being used. I could check these other 3 and they would not be used. If I had a call for heating and waited for the sequence, that's when we'd see this blue speed or medium low speed energize the fan motor. So that's how our speeds are working. Now one thing I want to note is when you're checking multiple speeds of the motor and you check voltage between neutral and any of these terminals, you're going to read voltage between all the terminals because the electricity is backfeeding through the motor to the other components, which is why we can only energize one speed at a time. I'm energizing right now high speed. Then we'll disconnect and connect here, or disconnect and connect here. We can only run one speed at a time through one of these legs and back home. So if I check voltage, because of that backfeed, we're going to show voltage on all of these. So between common and or high speed and neutral, I'm showing 121 volts. And if I check between neutral and high speed, I'm showing 121 volts. Also between heating, medium low, 138 volts. And between fan, I get 178 volts. And between unused, 156 volts. If you see, the voltage actually increased because these unused windings are actually generating electricity and it's reading back EMF. But there's no place for it to go because the switches, these relays, are open. So the only way we're going to check speeds is we're going to use the amperage of this. So that's how this multi-speed motor works. The capacitor, we'll check that a little bit later. We're going to disconnect all the voltage, discharge that capacitor before we check it. Now to our transformer, the same way we checked it, we see that we have voltage coming to our transformer. And we have 121 volts going to our transformer. Then we check our secondary voltage coming out of the transformer. And we have 27 volts coming out of the transformer. But we can also check that same voltage with these terminals on our fan relay. If I check between R and C, we end up showing 27 volts. And I can check between R and any of the other terminals, even though it's not calling, there's a potential 27 volts. We have also 27 volts. We have 27 volts. So we have 27 volts between all of those components. If you notice, I disconnected the call for cooling, but the fan motor is still on. These control boards have a time delay built into them where they'll keep the fan on to get that extra cooling, so to speak, out of the evaporator coil. We're moving air across that evaporator coil. The refrigerant's still flowing as it's equalizing, so the idea is it makes it more efficient. We hear the click of the relay, this fan motor shuts off. So all of these wires, once you break them down specifically, what am I looking for? What does this component do? It's very simple to diagnose it. Next thing I want to do is talk about this capacitor real quick. So what I'm going to do is disconnect our power and never assume that it's disconnected. I also want to use my meter and check. I want to check this bottom number for volts between my neutral and my primary, and it's showing 0 volts. So now it's safe to work on. So if I look at my capacitor, it's a very common fail part. So what I'm going to do is disconnect these 2 wires of my capacitor. And I'm not going to touch the metal because I don't know if it's holding a charge or not. So this is our capacitor. Now before I check this capacitor, I want to discharge it. I'm going to use a 20,000 ohm 5 watt resistor. I want to make sure I hold just the porcelain, and I'm going to touch these two terminals right here and discharge this capacitor. Now alternatively, if you don't have a 20,000 ohm 5-watt resistor, you can set your meter for voltage, turn it to DC, and you can let it discharge through your meter. In other words, it showed me a voltage just for a little bit. It allows it to discharge through the meter at a very even rate. So I'm going to set my meter to capacitor. So capacitor, this one I can't read upside down. Here's our symbol for capacitor. There's multiple different ones, so I'm going to use the select button. Right now it's automatically on ohms. I'm going to press select. Still on ohms, select. That's for diodes. Select again, it says NF. That should be UF for microfarads. And I'm going to check the capacitor by firmly holding one lead and the other. I'm going to wait. It's using the battery of my meter to charge the capacitor. Now it's reading 7.08 microfarads. So we're going to read on the capacitor itself, and the capacitor is rated for 7.5 microfarads with a plus or minus of 10%. So let's see if that capacitor is within range. What we're going to do is use a calculator. And we know at 10%, so I do 7.5 times 10% equals 0.75. So that means I could be as high as 7.5 plus 7.5. I can be as high as 8.25 or as low as 6.75 and still be good. So this capacitor, even though it's slightly lower, it is still good because it's within the plus or minus range of this capacitor. So that's how we check the capacitor. We put the two wires back on. It's safe to touch now because we know it's discharged. Now you're going to hear people discharge capacitor with a screwdriver. You want to be careful of that because if you're doing it with the screwdriver, if it's charged up, the electrons going from one side to the other can damage the capacitor. So when you're working with a capacitor, you want to make sure you discharge it with a 20,000 ohm 5-watt resistor or through your meter set to DC volts. So in this case, I prefer this because it's faster. Checked it, put the wires back on. We're ready to power the system back up. Now you saw me check amperage to see do we have a flow of electricity. But there's another thing we want to do with that amps. I want to check the amps of this motor and compare it to the tag of the motor. These motors are going to have a rating set for it. And this motor tells us the rotation, the horsepower, and right over here it has the amp rating, 7.10 amps. I want to make sure I'm not overamping this motor. So if I'm checking the amps of the motor, I want to make sure I'm below that number. If I'm above that number, it doesn't mean the motor's bad. I need to check the airflow. I need to check the evaporator coil. Make sure I'm getting enough air through there. I need to check the blower wheel, several things like that. And if all of that's good, then I start looking at the motor itself. On this one, there's nothing else to really work with. We have a very simple motor. So if I'm overamping on this motor, it's usually going to be the bearings, and we got to change out that motor. So very simple components to check. We can also check the amperage to our combination gas valve, but because it is low voltage, it doesn't give us a very accurate reading because it's a very small flow of amperage. So what we can actually do is take this wire and wrap it around the meter, and that doubles the magnetic field. So whatever number I get, I divide that by 2, and that gives me a very accurate reading of the amps. One last thing before we get done is we want to see this flame sensor. They notoriously get dirty, and if we look at this flame sensor right here, there's a lot of buildup on here. See, it's nice shiny metal, and here it discolors. As the flame burns across this, any of the dust that's in the air, the flame itself burning causes a buildup on this. What we want to use is a type of Brillo pad or abrasive pad to clean that off. Never use sandpaper because the sandpaper actually has the glass that can leave residue on here that actually turns to a glass coating. The sand from the residue turns to a glass coating, and it can give us a coating on there that doesn't allow the flame rectification to work. And the exact same thing for our spark igniter over here. On this spark igniter, if we pull this off, we can see the discoloration between these 2 points on here. So that's one thing we want to keep in mind, is make sure we keep those cleaned.